now we have developed an expression for the time derivative of the velocity error. The other term that is slightly involved is the time derivative of the attitude error. So let us now delve into how this can be done. Again, I'm going to compare the true attitude derivative with the nominal attitude derivative. And again, I'm also going to use this separation into what Sola calls small and large parts. So I start by making some useful definitions. So I'm going to define the large part here, large part angular velocity, which is the measured angular velocity minus the angular velocity bias. And why do I do that? Well, it's because this difference is actually what is used in the derivative for the nominal attitude. So that one was given by Q and Q dot. And then it's the same as 1/2 Q. Quaternion product is omega. So here I use this shorthand notation for doing the quaternion product between a quaternion and a vector. This omega is really supposed to be sort of the vector slot of the second quaternion, but we just write it like this for simplicity. Then I'm going to also define the small part of the angular velocity, and that I'm going to define like this. So I have the error of the angular velocity bias, and then I have the noise term. So this thing I call delta omega is in contrast to we talk about the delta V. Is not something that we actually ever implement. We don't. Omega is not part of the state vector, but it's useful in the derivation to have this. So then I'm going to express the true angular velocity in terms of these entities. So the true angular velocity is the measured angular velocity minus the true bias minus the IMU noise that comes into the measured one. And then I can decompose the true bias into the nominal bias and the bias error. And just to emphasize how I'm splitting this up in the large and small scale contributions. Okay, so then I'm going to start looking at the attitude derivative. Here the point is to have several different expressions for the true attitude derivative and compare these. So on the one hand, I can take the true attitude, and then I have a differential equation for that in terms of the true attitude and the true angular velocity. So it looks like this, and then I can relate this to the nominal and error attitude simply by splitting up this QT. So that's one possible expression. Another possible expression is to think of this true attitude as because I said that's the same as Q, Italian product delta Q. So I can differentiate this thing and use the standard product tool for differentiation, which I also can use for the quaternion product. So then I get again expression for Qt dot. So now then when I differentiate this, I get first Q dot, then I call it delta Q, then I get a Q, quaternion product delta Q dot. And now I have some knowledge about this thing, Q dot, that I can insert here. So that's this thing over here. Then this omega I defined comes in. And the second thing I don't do much with here, because delta Q dot is after all what I'm really looking for. That's the one I would like to have an expression for. Now if I compare all the things I have here, I have an expression here and I have an expression here. And in all of this there is a pre-multiplication with a Q. So this Q I can remove. When I remove that in this last term here, I'm left with only delta Q dot. That means that I have some expression for delta Q dot. And yeah, let me just multiply this by 2. So then I have this thing, delta Q product omega t. And then I have this thing, so if I get minus omega quaternion product delta Q without any t. So this what I now would like next is to combine those omegas and see if I can do anything sensible with that. And then I would like to think linearity, and to think linearity I would like to have this expressed as matrices instead of these quaternion products, because I know I can do that. I have some matrix expressions for quaternion products. Then this turns into something looking like this. So this is the matrix form of this first thing. And then I want the matrix form here also that leaves me with delta Q at the end. Then I just find these things from the book. Then now I can start to subtract things in the matrix elements. then I get minus t minus omega exposed there. I get omega t minus omega. And then I get this inside. I can just put things inside the S matrix. Minus S omega t minus. Sorry, there should have been a minus over here. Then this makes sense. Now I don't really want my delta Q here because that's not part of my error state. It's delta theta that is part of my error state. So then another approximation comes. Not with the matrix, that one remains the same. Should have plus here. Yes, plus omega. And there the approximation comes. I switch delta Q with delta theta divided by 2. Now I need to recognize what these different omega combinations are. So let's see, omega t minus omega. What I have over here. So if I have omega t and I subtract this thing, then I'm left with this delta omega. Then I have omega t plus omega. So if I have this and I add, and I have 1 omega from omega t, and I have delta omega from omega t, and then I add another omega. So I'm going to get 2 omegas and a delta omega. Yes. Then I'm again in my delta Q dot here. Again, what I'm interested here is what happens in the vector slot of this thing. That's what governs my evolution of the error angle. So here I have 2 delta Q dot. So what is it that we get there? Well, this should correspond to my delta theta dot. Yeah, of course, this is approximative, so I have to write approximation anyway. Then I'm going to get this times this. So I'm going to get delta omega. And then I'm going to take this right, but it was not clear enough, delta omega. So then I take this times this. I have this second order term, delta omega times delta theta, which I forget. S of 2 omega times delta of half. And then I can insert what this 2 omegas actually are. Same as omega n minus omega b delta theta. Yeah, so the 2 here cancels with this 2. Delta omega b for the bias, and finally omega n. So this is from this part. And then again I have something that is completely linear now in all the aerostate terms, which is this one, delta theta and delta omega b, and again driven by a white noise process. So then I have the derivatives of both the attitude error and the velocity error established.